So welcome you back once again, dear students, in TEM Part II. If you will see the electron beam, the path of electron beam, that it comes direct from upward to downward direction. It starts from electron gun and it is magnified by means of these condenser lenses, and then it comes up to objective lenses, and then finally up to projector lenses. So if you will see the lateral view of electron interaction with the sample, then you will find in this way. And when it is passes through transmitted through sample or a specimen, then we find the view of electron movement in such way. The diffraction contrast, various diffraction attributes causes the diffraction contrast, in which the concept is this concept is useful to find various crystalline disorders like stacking faults, dislocations and precipitates. Extinction or bend contours and thickness fringes are also studied by this mechanism, because where the concentration of electrons which are transmitted through the sample is high, that part that looks like a bright part, and where the concentration of transmitted electrons remains less, it means the maximum number of electrons are blocked in those places. Those looks like the dark places. The vacuum is required to achieve an insulating medium nearby the field emitters between anode and cathode filament. The vacuum is used to suppress the undesired electrical discharge inside the electron gun, and it enhances the electron travel path from 1 centimeter to 6.5 meter in atmospheric pressure in vacuum of 10 to the power minus 6 Pascal. If the vacuum is further increased from 10 to the power minus 6 to 10 to the power minus 7 or minus 8, then the intensity of electron beam that enhances up to maximum extent. Under vacuum, oxygen eliminated from filament surrounding which suppresses the possibility of filament oxidation. Under vacuum, the chances of interaction between electrons and gas molecule in the main column improves the picture quality and decreases the sample contamination. The electron gun requires a vacuum of 10 to the power minus 9 Pascal, while projection chamber and camera needed 10 to the power minus 5 Pascal. So these are some different type of pumps which have their capacity to create the vacuum level. If you will see the rough vacuum pump, then it is able 100 to 0.1 Pascal. Low vacuum pump 10 to the power minus 1 to 10 to the power minus 4 Pascal. High vacuum pump 10 to the power minus 4 to 10 to the power minus 7 Pascal, and ultra high vacuum pumps less than 10 to the power 7 Pascal is possible by using these type of pumps. So sample preparation, that is very tedious, very tricky part of TEM. The sample preparation requires enough experience. Sample insertion into TEM is also tricky. The disc shaped thin sample should be 3 mm diameter to make it convenient for TEM. So you will see that the sample cutting by mechanical polishing or dimple grinding process, when thinning continues and it creates a fine hole, then nearby that whole area, the thinnest part which have the thickness lower than 100 nanometer is cut, and that is used as a sample for TEM. In case of inorganic sample preparation, the electropolishing or jet polishing is used for metallic sample, and sample is act as an anode inside the electrolyte cell under light voltage. Metal dissolved slowly from anode and slowly deposited on cathode side. In this way, the thinning process remains continued. The regions around the hole are thin enough to be used as sample for electron transmission inside the TEM. These samples are cut in 3 mm diameter disc form. These samples are often called as the foil. Then the foil is revolved to get the homogeneous thinning on that particular part. So jet polishing of metal take place like that. So drill a 3 mm cylinder and then cut into disc and grind it. A disc is mounted on a jet or losing machine, and is electropolished until a small hole is made. So at the beginning, a thin slice cut by using diamond buffering blade. One side of this thin disc is polished and then sticked on glass slide carefully. An uncovered side is ground down by using SIC paper of various grade to bring its thickness up to 100 micron. Then 3 mm disc is machined ultrasonically by opting ultrasonic drill with some abrasive ceramic powders. In this way, this disc is dimpled by gentle application of polishing paste with the help of rotating wheel. The sample is prepared up to maximum extent, which is finally milled by ion beam milling process. So in this way, when the a hole that start to appear in a particular disc, then nearby area of that hole that is cut down and that is mounted on a sample holder. So plasmid ion beam makes thinning process very fine and easy. Two guns used sometimes for uniform thinning from both sides simultaneously. Sample rotates to avoid any roughness on any particular place. So uniform grinding is required. At a hole, as a hole appears, the surrounding region of hole considered for TEM as a sample. Organic sample preparation, the sample are soaked for 30 to 120 minutes in toxic chemicals like glutaraldehyde, paraformaldehyde and CaCl in codylate buffer. Calcium chloride containing coca dilate solution for 1 hour. Then sample washing takes place and then again it is followed by 2-hour washing in osmium tetroxide. Then glycogen and stained lipid membranes are treated with potassium ferricyanide and washed with distilled water. Washed sample are again treated in dark for 1 to 2 hours with aqueous uranyl acetate, which is combination of 3 chemicals in which the methanol, ethanols are the prominent, and washed again. Finally, the sample are fixed. Then dehydration of sample is the next stage of sample preparation. Then it is again cleaned by ethanol acetone to suppress the lipid loss by soaking for 10 to 20 minutes. The soaking of sample concentration 10 to 20 minute soaking and 70% ethanol, followed by 10 to 20 minute soaking in 90% ethanol, again followed by 10 to 30 minute soaking in 100% ethanol. So in this way, the 5-minute soaking in 1:1 mixture of ethanol and propylene oxide, which is followed by 10 minute soaking in pure propylene oxide to get the complete dehydration. In this way, the dehydrated and fastened specimen is then said to be embedded in epoxy. So generally, a polymer resin like araldite hardener, which is used, plus an accelerator like BDMA, that is also used. Sample is left for conditioning and fixing at 60 degrees centigrade for 48 hours. Sometime it is preferred to keep the sample for a few days also. So after polymerization, steel, glass, sapphire or diamond blade containing microtomes are used to cut very thin slices. So application of TEM, TEM is used to find the composition at crystal structure, local chemistry of material, morphology, and then structure and properties like general polymeric, biological and metallic materials. They are used at very fine level, orientation, chemical composition of various phases, precipitates and contaminants through diffraction pattern. And characteristics, X-ray and electron energy analysis can also be possible by TEM. Morphological study like various sections of material, fine powder suspended on thin film, small organism like viruses, bacteria, frozen solutions. The study of these type of materials is possible. Three-dimensional images can also be formed by tilting the sample on sample holder with the help of sample holder. So analysis of composition and presence of chemical bond, that is also possible by using some additional detector. Electron energy loss and microanalysis by integrating the spectroscopic technique. Physical manipulation of sample during Scanning by TEM is also possible, like compression and bending of sample to estimate the mechanical properties. Cryostat studies in frozen condition, that can also be studied, and EDX can also be integrated to find the X-ray diffraction analysis along with TEM. Apart from all these merits, the TEM has some limitations also. Colored images cannot be obtained, but can be modified to introduce colors by using some softwares. Scanning is possible only 100 to 200 nanometer slice thickness, because electrons lose their intensity when penetrating slice which are thicker than 200 nanometer. So surface information does not possible, but when the electron transmitted through the material, so they get interaction with the electrons, protons, neutrons, which comes in the way of that particular electron beam. So finer morphological informations are evolved by means of TEM scanning. Difficult to image the charged atom which are mobile in a mixture like sodium ion, which are volatile in nature and get interacted in presence of powerful electron beam, because the electron beam impart a ample force on charged material. So such type of materials may create problem during scanning under TEM. This is a typical sample holder in which the frame is there, flexible PCB is there, push bar is there to push the sample holder inside the machine. This is FVC connector. These are the wire bonds where the sample will place. This is MEMS shape, and this is the eccentric axis. This is a tilting table where the tilting can take place if the scientists are interested to get the three-dimensional images. This is torsional spring to for firm catching or placing of a specimen on sample holder. So this is all about the TEM part 2. Thank you very much.